Welcome Mechanics of Materials students. In this lecture we're going to be going over some key principles from statics that are going to form the baseline of how we deal with problems once bodies are no longer rigid and are deformable, which is the main topic of the study of mechanics of materials. So we're going to start right off with two bodies. We have body A here over on the left, and it's being acted on by a bunch of forces and couples, F1, F2, and in couple 1, the double-headed arrow, of course, being a couple or an applied moment. And we can reference the location of all of those points of application of force to this coordinate system. At O, we have an XYZ coordinate system. And we can create a resultant or net force by simply summing all the forces. So we can write the resultant force of all of the bodies, or excuse me, the resultant of all of the forces acting on body A as just the sum of all the forces, and then we can sum the moments acting around point O, remembering moments have to be referenced to around what? So we're going to reference the moment due to the forces acting about point O plus the applied couple, which doesn't have to be referenced to a point. We sum all of those, and of course we use our cross product to calculate the moment of each force at a radius from point O to its own point of application on the rigid body, and those equate to the sum of the moments or the resultant moment on body A. Now if we happen to have another body, B, shown over here on the right, with a bunch of other forces and couples, different, acting at different points of application, different radii from our same point O, our origin of our coordinate system, we can write a similar expression for the force resultant on body B and the resultant moment on body B. Now we can say that this concatenation of forces and couples over here on acting on body A are equipollent or equivalent to those acting over the ones acting on body B if the resultant force RA is equal to RB, and that's a vector quantity, of course, so it's going to have to be pointing in the same direction and have the same magnitude. And of course if the vector expression for the resultant moment acting on body A is the same as acting on body B. So that's just a review of what does it take to have an equivalent force moment system. That's force equipollence. So if we're in 2D, we're going to end up with three equations that will establish equilibrium given any system of forces and moments. So we'll have the sum of the forces in the x and y direction, and then we'll have the sum of the moments about the z-axis. If we have a 3D coordinate system, we'll have 6 equations of equilibrium, sum of the forces in the x, y, and z direction, and then we will have 3 vector directions of moment. So we'll have the moment about the x, y, and z axes. All 3 orthogonal axes. If we are in static equilibrium, we will not be accelerating. So that's the key condition of equilibrium, that the sum of the external forces is 0, and therefore we won't undergo any translational acceleration, and the sum of the external moments is 0, which means that our body won't begin to rotate. We'll have 0 rotational acceleration. So if a body is rigid, that, the sum of the forces being 0, or the sum of the external forces being 0, and the sum of the external moments 0 is sufficient to define being in static equilibrium. But we're going to be looking at things that aren't rigid. Mechanics of materials mainly concerns itself with bodies that can deform and understanding how they deform. So we won't necessarily be in equilibrium simply because the sum of the forces and the sum of the moments that are applied to our deformable body are 0. Why? Because the body will undergo deformation or strain instead of just having all of the distances between all of the points in the body stay the same as forces are applied, which is the definition of rigidity. So thinking about if you're not in equilibrium, and thinking about the equations that we'll get from equilibrium, which will factor into how we describe deformable bodies just like we did rigid. We'll just do a quick review of the three different situations we can have with regard to equations and unknowns, and with regard to whether something's in equilibrium or not. And again, this can hold for deformable or rigid bodies. So if we have more independent equations than unknown forces, so we can write more equations of equilibrium than we have unknowns, which would kind of indicate you have fewer forces than you can write an expression for, like maybe you won't have any forces in the x direction and the body could then accelerate in it, or you might have a net force. Just as an example, you will generally be in what's called an unstable or incompletely constrained condition, which means chances are you have a net moment or net force and you will accelerate. You are not generally in equilibrium. There are cases, for instance, if you didn't have any forces in a given direction, even though you have more equations than unknowns in that direction, you wouldn't necessarily have a net force, but more chances than not, don't assume that you are necessarily in equilibrium. That's why it's called being unstable. You could be statically determinate, which is the case for just about everything that we've probably gone through in statics, in all of our studies of statics, where we have the same number of independent equations of equilibrium as unknown forces. So that 3 in the case of 2D systems and 6 in the case of 3D systems. In that case, the system is in equilibrium. Whether or not we can solve for those forces and moments is another thing. But the system's in it is in equilibrium. We just don't know what the magnitudes of everything are to satisfy those equations, but nothing's going to accelerate. Last but not least is statically indeterminate, where we have fewer independent equations than unknown forces. So we've got extra forces, hence it's sometimes called an over-constrained system. We're grabbing onto it in too many places. Most of the time it will be in equilibrium, but not necessarily. We can say that our laws of motion are insufficient to determine. In a lot of cases, this state of over-constraint can cause bad things to happen with respect to fracture. We'll have that kind of situation approaching what we'll later learn is called plane strain conditions, where it's hard for things to yield. So that would be kind of a mechanics of materials, future and material science idea of an over-constrained system. But simply from the standpoint of numbers of equations and unknowns, if we end up having more independent variables, more forces, more moments than we have equations to solve for, we are indeterminate. We may be in equilibrium, we may not, as opposed to unstable, where we're more likely than not in equilibrium. Okay, so that's kind of statics in a single page. So let's pan back and just walk through a few quick examples to kind of warm up our equations of equilibrium mental muscles before we start diving into definitions of stress and strain for mechanics of materials. Because in all cases, we will need to know what forces and moments we are actually applying to a body before we start looking at how those forces and moments will work with the geometry of the body to translate into an applied stress, and then how the material properties of that body are going to react to that stress and result in a measurable strain. So it all starts with what's going on with the applied stresses, the applied forces, which will result in applied stresses, and so that all flows out of our conditions of equilibrium. By the way, we are starting with a review of statics because even though mechanics of materials definitely applies in cases where something's accelerating, obviously you can have something accelerating and deforming. Those of you who might remember the idea of the coefficient of resolution in impact back in your studies of dynamics, that was actually concepts of deformable bodies and dynamics being applied. Something's decelerating and deforming at the same time. In most cases in this course, we will be assuming that something is in static equilibrium and then using the assumption of equilibrium and solving for what has to happen to maintain that equilibrium to actually derive the expressions that we'll use later on to relate, say, deformation and strain, and the Hooke's law expressions for elasticity and strain energy. So should have maybe started with that, but we will definitely go back to, if you've just recently taken dynamics, this will be a step back into the world of static equilibrium, but relieving the rigid body criteria. So eventually, of course, in engineering practice, mechanical engineers, for instance, will probably use a combination of dynamics and mechanics of materials. Maybe civil engineers hopefully are designing things that aren't going to accelerate, so they may do more pure mechanics of materials. But everyone will end up doing some kind of blend, if for no other reason than we all deal with vibrations, which are a mix. But we'll be focusing on everything in static equilibrium for the most part, unless otherwise specified in this introductory course in mechanics of materials. So that said, let's take a look at a couple of rigid bodies here, A and B. So we have a force pushing this wedge A, which is at an angle B or beta with respect to the horizontal, and these are frictional surfaces. And so we want an expression in terms of beta and the weight of block B. Supposedly the weight of the wedge is negligible, and the coefficient of friction on both surfaces, it's the same for what force is needed to just initiate movement of wedge A to the right. So this would be kind of the minimum force to maintain this system in static equilibrium, because obviously your block B is pushing down, and so in order to keep things just on the edge of moving to the right, that would be defining equilibrium. So a good place to start for any statics, any equilibrium condition, is to look at the conditions of equilibrium of what I call the whole body FBD, where we neglect any kind of motion or interactive forces. We kind of suspend Newton's third law between contacting bodies, and we just we kind of do a thought experiment where they're welded together, and we look at the forces and moments that have to be applied outside that whole body in order to keep it in static equilibrium. Because if the whole body's not in static equilibrium, the component parts certainly are not. So I start with what I call the whole system FBD, which I'm drawing down here. I've deliberately drawn a stylized view without showing the actual connection to prevent myself from trying to prematurely apply Newton's third law. So we've got the weight force on body B acting downward. We have normal forces at the vertical and horizontal walls. We have frictional forces opposing motion, and so I've drawn them in the directions that would oppose the motion that would be caused if we pushed wedge A to the right. So remembering with friction, we have to know what direction something would move, so we know what direction to write the frictional force to oppose that motion, because by definition, frictional force is always opposing motion. So if we push wedge A to the right, we'll have the frictional force between A and the horizontal acting to the left, and of course pushing the wedge A to the right will result in block B being pushed up, so its frictional force would be downward. We don't have any dimensions, so we can't write any expressions for moment, so we're going to kind of hope that maybe we don't need them and we can get by with just sum of the forces in the X and Y being equal to 0. So we can do that here and write the sum of the forces in the X. So we have P acting to the right, and right I've defined up here as positive, and upward is positive. So we have P minus FA minus the normal force at B all equaling 0, and we can invoke our relationship between normal force and coefficient of friction at imminent slip, because we were told, hey, what's going on right before it starts to slip? So I can drop in that mu NA instead of FA, and I can do the same thing in the y direction. So I've got NA working upward, weight working downward, and then frictional force B, or mu NB, working downward. So set those equal to 0. So far we have 1, 2, 3, 4 unknowns. No, we know W. We have 3 unknowns, excuse me, and 2 equations. Well, that was so far. Let's see, what would we call that? We have 3 unknowns and 2 equations. We are statically indeterminate. So let's see if we can use Newton's third law and write an expression for equations of equilibrium of one of the 2 bodies. So we're going to pick the wedge only. So that's going to give us another known, which is that angle beta. So we can write an expression for the force between the 2. I've called that Q here. And that's, unfortunately, we're adding another unknown. But hopefully we'll be able to add more equations than we do unknowns, at least a 2-to-1, and give ourselves a statically determinate system. So I have, because of the configuration here acting at a point where the force between the 2 bodies we know is going to act perpendicular to the wedge, and we were also told that we have some friction between the wedge and the block, and that has the same coefficient of friction as the surfaces. So we have a normal force Q coming down from block B, so that's representing the normal component of block B's weight. But because we've got other frictional components, we don't. It's not just the weight; it's everything else that's acting on B that would be opposed by A. So it's unknown Q. And then we have a frictional force acting parallel to the surface. So Q is another unknown because it's not just the geometric resolution of the weight, because block B has other forces acting on it. So we have the same frictional force acting to the left on the wedge. We have, again, the normal force acting upwards, and now we have the same force P acting horizontally. This P, of course, being the same as this P. Okay. Again, we can't write a moment expression, but we can write 2 equations of equilibrium in the form of the sum of the forces in X and Y. So we've got that in terms of X. We have P working in the positive X direction, mu times the normal force at A acting negative X direction, and then we have Q sine B acting negative X, and then we have the cosine of mu Q acting in the negative X. And hopefully I said Q, not mu Q for the sine component. That's just Q, not mu Q. Right there. Okay, so that's the X tally, and more importantly, we've added one more equation, but we've added another unknown. So as of this equation, we're 1 for 1. We're still stuck with now 4 unknowns and only 3 equations, but we get another equation of equilibrium in the form of the sum of the forces in the Y, which are going to be similar. We don't have Q, or excuse me, we don't have P, but we do have the other trigonometric components of mu Q and Q. So that's 4 equations, 4 unknowns. So our unknowns being P that we wanted to solve for, Q, the A to B normal force that we introduced via Newton's third law when we did the wedge only FBD, and our 2 normal forces with the wall. Remember, we were given the weight, we were given a coefficient of friction, we were given the angle beta. So if you wanted to actually go through and solve it, you would find that this expression is the relationship between the force, the horizontal force pushing to the right, P needed to get the wedges moving, given these weights, angles, and coefficients of friction. Okay, let's take a look at a truss. Just to review, the definition of a truss, of course, is a series of rigid members of which all are two-force members that are in static equilibrium. Usually, anyway, we'll be able to get solutions when it's in static equilibrium. So each of these members is a two-force member, so we can represent the forces in the member as simply compression or tension being directed in the direction that the member itself is pointing. So the geometry of the truss actually gives the geometry of the forces of all of the members in the truss. As you recall from statics, there's two main ways of solving for all the forces in a truss. I should say solving for any force in the truss. One is the method of joints, where you basically put each joint pin, so to speak, in static equilibrium and solve for the forces that are directed in the directions that the members are pointing based on the geometry of the truss. The second is the method of sections, which we used here, which is great when you need to only solve for a couple of members, and that involves sectioning the truss in different places that cut through the members that you care to find something about. And in this case, I believe we've cut them like that. Those are our two sections. So in this case, we're asked to find the forces in members BC and in members CD. So given that we didn't need to solve the whole truss, we only needed to find the forces in these two members, the method of sections really makes more sense. Now, regardless of which method you use to solve your truss or the members for which you need the forces in the truss, it is always a good idea to start with a whole truss FBD and get the support reactions. And in almost every case, this will be solvable with a single set of equations of equilibrium, especially if the truss is what's called simply supported. So in this case, we have a connection at A, so it can apply a force in the X direction and the Y direction, and we have just a kind of a roller bearing supported E, which can only give a force in the vertical direction. So we can write equations of equilibrium in the X and Y direction. Moment about point A allows us to solve directly for our force E in terms of the applied external forces. So we've got 5 kilonewtons horizontal and 10 kilonewtons vertical. So if we take our offset dimensions, are 7.5 meters and I believe it was 10 meters here vertically. We plot those into our moment equation, solve for E, and then back solve, get our vertical support force at A and our horizontal support force at A as well. We take those horizontal supports and horizontal and vertical supports for point A, and we use them in our left section. So I'm going to erase this other section here. Erase this one for now. So having solved for our support reactions, we're going to look at this section here because it cuts through BC as well as some other things, and so we can draw an FBD of just this left-hand side of the truss, everything on the left-hand section. So when we cut through a member, we replace it with the force that it would impose on the remaining section. So here's point A down here, and we can take the vertical and horizontal support reactions that we solve for and apply them to point A. And we just got some geometry, and then we have BC, FC, and FD representing the forces due to the members that we cut away. If we take the moment about point F, we have one unknown because the forces FC and FD go through point F, so they can't create a moment around it. So in one equation with this section, we can get the force due to BC using the moment, the sum of the moments about F. So we have BC, and then we have only the Y support reaction are capable of producing moment, because the 5 kilonewtons and then FC and FD are collinear. They converge on point F. They can't produce a moment. So using that, we can get our force through member BC. We can apply the method of sections again for our CD. I'm going to erase my first section here. So I can apply the method of sections to CD, and I'm going to go ahead and look at the right-hand side. So here's my section, and now I'm going to look at everything on this side of it. And so we have that drawn down here. So we have, again, we've got our supported E that we got from our full body FBD. 10 kilonewtons is applied, and that's applied at point G. And then we have the sections we cut through CD, DF, and CG. Those are all represented by forces that are pointing, that are oriented in the direction that the actual section of members were oriented. And if we take a look at this, we notice that we have two unknowns that are completely horizontal. They don't produce any forces in the Y direction. So the 10 kilonewtons downward, 8.75 kilonewtons upward, the difference in those two vertically oriented forces has to be compensated by whatever is going on with the normal or the vertical component of CD. So we can take the sum of the forces in the Y of this section and get the magnitude of and direction of the force in CD, and it turns out to be 1.29 kilonewtons in tension, and BC was 0.625 kilonewtons in tension. So an important thing that as we look forward into mechanics of materials, the method of sections is a foray into actually looking at internal forces, probably the most simple case of them. But we stepped outside of the body and actually looked at the internal forces in that member that would allow the two separate sections to behave, and we joined them with Newton's third law. But that was an example of something we will definitely continue in mechanics of materials, being concerned with what are the forces inside a material, and how does that material have to react to counteract those forces such that the whole material stays in static equilibrium. So we're going to see that again. I am going to skip this one in the lecture. It's a fairly straightforward frame. We end up having a two-force member within it, but this is another pretty straightforward example of drawing FBDs incrementally of different portions of a connected body in order to solve for what we want. Just to give a brief overview, we were asked what force does the member EF exert on this kind of longer roller pinned CED. And to do that, of course, we have to take a couple of steps. We have to make sure our upper bar is in static equilibrium, and that gives us our vertical up-down force at D, which of course we can translate over to an FBD on our beam CED, and then use the fact that EF is a two-force member to represent it by a single force at a known angle and the sum of the moments. So again, even though this whole body is not a truss, member EF is acting like one member of a truss in that it is a two-force member, and so that gives us information that we need to solve our equations of equilibrium. But otherwise, solving for force D and then carrying it down to another FBD is just a simple application of Newton's third law, just like force Q between the wedge and the block on our frictional problem was the link between the two separate but related bodies. They're exerting equal and opposite forces, equal in magnitude, opposite in direction forces on one another, contact forces. Okay. Looking at something that we are definitely going to see again when we look at beams. We have, this is a beam that has a distributed load and it has a point load, and it's being supported on, it's again simply supported. We have an upward kind of bearing force at B, and then we have a pin force at A. We know it's a pin because it's not exerting a couple, and it is capable of exerting forces in two directions. And somebody wanted to know what are the forces at 2 meters right here. So someone said, if I cut that beam apart at 2 meters, what would the forces in a direction parallel to the beam axis, perpendicular to the beam axis, and moment about an axis sticking out of the page, what would those be in terms of what forces and moments would have to be exerted on the other end of the beam to keep this side in static equilibrium and vice versa? So this is all concerned with internal forces at this point. So again, this is a typical shear and bending problem for a beam. Again, we will definitely see this again in our study of beams in more detail. But just to step through what we've already learned about this from statics, we would, again, as in almost every case, we would solve for the support reactions. So that's this FBD over here, where we've taken our distributed load and did a little quick shortcut, did a 1/2 base height to get a magnitude. We could have integrated, but we would have gotten the same answer, and we've positioned it at 1/3 of the distance from the long end, the long edge. Again, we could have done our integral to find the centroid of this distributed load shape, and we would have gotten the same thing. So we have 4,500 newtons, equivalent resultant force representing that triangular distributed load, positioned 2 meters from point A. And then we've resolved our 890 Newton point load or concentrated load acting 1 foot to the left of point B, and we've resolved that into 445 newtons upward, 771 newtons parallel to the beam axis. So that allows us, with the sum of the moments around A and then sum of the forces in the x and y direction, to solve for AX, AY, and B. So those give us the starting and ending points for integration when we drop in our relationships between distributed load Q, or load per unit length along the beam. That's what this load is. It's 0 newtons per meter at point A, and that's 3,000 newtons per meter at a 0.3 meters to the right of A. So if we were to write like a line equation to represent this line, it would be 1,000 newtons per meter squared x. So when x is 3, this is 3,000. When x is 0, this is 0. So we know that if we integrate that from a starting point to an ending point, we get the difference in the shear stress or stress parallel to the cut edge of that beam if we were to cut it wherever at x. Between the shears, we'd get effectively, when we integrate this, we'd get the difference between the shear stress at, in this case, 0 to the shear stress at whatever x we go to. In this case, we're going to go to 2. So We integrate the right-hand side and we get 500 newtons per meter x squared. And then we integrate the left-hand side and we just simply get v at x minus v at the lower limit of integration, which is v at 0. Here's where we use our support reactions, because now we have to solve for, well, what is the shear stress in that beam all the way over at the x support? Well, it has to be whatever is opposing the full magnitude of the support reaction at x. So basically, if I were to take that beam and cut it in a teeny tiny little sliver just to the right of the support reaction, I would find that the beam all the way to the right of that tiny little sliver that's practically sitting right on top of the A support would have to be exerting a downward force that's equal to the upward force of the support, or the sliver would not be in static equilibrium in the y direction. So that gives me v, that idea, and a value for a sub y gives me v at 0 as being negative 2611 newtons j hat. So it's working downwards, downward direction. So I can just add that as basically the b-intercept of my line, the y-intercept, y equals mx plus b. Actually, we have a quadratic equation, so forget I said that. It's not a line. But anyway, I can add that to both sides. We add a negative 2611 to both sides. So here's the expression for shear stress, or stress acting parallel to the cut edge of that beam at any x, at least at any x up to the end of where that distributed load is active, and at 2 meters we're definitely within that. So if I wanted to know the shear stress at 2 meters, all I'd have to do is drop a 2 meters right in here for x. And in fact, when I do that, I get 611 newtons downwards. So to get the moment that's being exerted on that cut end, likewise, I know that if I integrate my full expression for v sub x, I will get, between any two limits, I will get the difference in the moment being applied around that cut end between any 2 points. So the difference in the moment. So I do the same integration, but instead of integrating q, I'm integrating v. And it's the full v, including its lower limit. So I put that whole expression here, and I integrate with respect to x from x equals 0 to any x in this case, and I'll get the difference in the moment at any x versus the moment at 0. Now I go back to get the moment at 0. I go back and I consider what's going on at x equals 0. Well, I got a hinge. It ain't applying no moment, so there can't be a moment being applied from the rest of the beam, so I know that the moment on a cut edge that I would expose right just to the right of x equals 0, it has to be 0 as well. So that's 0. So the moment at any point is just this expression, which we've rewritten down here. So again, if I want to see what that is at 2 meters, all I do is put 2 meters in for x, and I get that value. Now how about parallel, or parallel is the axis of the beam, perpendicular to the cut face? So basically what would be an axial force acting on that cut edge? Well, if we come back up here, we notice that we had a point load that had a 771 Newton component in the positive x direction acting towards point B. And that's being applied or being opposed in terms of the whole beam by our A sub x support. So if we cut the beam anywhere between the A support and the application of this horizontal force component over here at 4 meters from point A, the internal forces of the beam would have to be carrying that 771 newtons, and so basically it would be carrying it in the positive x direction anywhere along there. And since 2 meters is between A at 0 and where we apply the 771 at 4 meters, we would say that the normal component of the internal forces in the beam anywhere along there is 771. So that's a quick and dirty review of shear, bending, and axial forces in a beam, going back to review our relationship between distributed loads, shear, and bending moment on any cut edge or cut end exposed as we go along a beam. We will definitely be, again, going back to that when we turn our attention to beams, and then leveraging this to move forward and look at things like deflection. Okay, so this has completed our quick review of statics. Statics in a few minutes. And what we'll be relying on going forward, we'll be using FBDs extensively and conditions of equilibrium to determine the external and internal forces, and to relate applied stresses to forces needed to put maybe a small body, something that we might shrink down to 0 size and take limits of, putting that into equilibrium, and then seeing what relationships have to arise between applied stresses in order to keep that little volume element in equilibrium. You'll see that again and again. We'll be doing FBDs on volume elements. And we'll be relying on the fact that, again, as a separate idea, most deformations are small. We're not looking at material processing here, where we're going to have huge deformations like you would in forging a metal or extruding something like a particulate polymer composite. We're looking at very, very small strains. So in a lot of cases, we'll be able to use geometric approximations for small angles, small extensions and compressions, and be able to make very accurate mathematical estimates, taking, say, the first term of a Taylor series expansion and simplifying our relationships and expressions. So you'll see that referred to as small deformation assumptions when they arise. And of course, in cases where small offsets can apply when we shrink a volume element down to 0, those will also be noted. So that is it for review of statics and key aspects of statics that we'll use looking ahead. So for future videos, we'll be jumping into definitions of stress and strain, stress-strain relationships via Hooke's law, and the concept of strain energy. We'll be applying those to bodies with axial loading, torsional loading, twisting, bending loading in the case of beams. We'll be looking at what happens when things aren't elastic anymore. We'll be looking at stresses and strains at different angles inside a body with respect to coordinate axes and directions of applied loads, how those impact when things are going to start yielding, no longer be elastic, when they might break. And last but not least, we'll look at strategies for using all of this to look at things that are statically indeterminate. That last category that we couldn't deal with in statics. We have a few tools for dealing with that now, and we'll look at how we deploy those. So looking ahead, and stay tuned for future lectures.